Let's talk about vias and printed circuit boards. Today I'm just going to talk about single-ended vias. Now when you want to transition a signal on a PCB trace and say you want to go from the top layer to the bottom layer, you can use a via to do that transition. And a via is just a metal barrel that you use to connect your signal between traces. Now when we look at electrical properties of via, the way to model that, or the way to think about it, is if you have pads that connect your layers, and those are typically capacitive, and then you've got your metal barrel that goes through your PCB, and that's typically your inductance. Now there's not much you can do about changing the inductance in the barrel of your via, because that's really dependent on how many layers you need to travel through in your transition. The pads, however, is really where you can change the impedance of your via. So if you're concerned about the impedance of your via and you want to impedance match your via to your PCB trace line, say it's a 50 ohm line, then by changing your pad and anti-pad clearance holes, that's how you can impact the impedance of your via. And there's literature out there, there's been a lot of papers and research done on that, and typically you will need a 3D field solver because of the way the physics are of a via properties in order to do this type of analysis work. But all the papers show that it's really the via pads that you can increase and decrease, and that'll allow you to get sort of a constant characteristic impedance. But the next question, this is a question that I see a lot of people ask, is, well, when do I need to worry about the electrical properties of a via in my system? When should I be worried if the characteristic impedance doesn't match? And that really has to do with the edge rate of your signal. And I think the best way to describe this is to think about a time domain reflectometry system, right? Or a TDR. So think about your signal that you're driving through your system and how fast that edge rate is, but not necessarily how fast it is at the I/O buffer or inside your chip, but how fast that signal is traveling once it reaches your via. So for example, if your signal goes through your package and then let's say it goes through 2 inches of microstrip trace and then it hits a via, well, what's the edge rate by the time it hits a via? It's going to be filtered and slowed down as it goes through your system. So for example, if you've got a microstrip trace that's 1 or 2 inches, that might have a total electrical delay of 300-400 picoseconds. Remember, vias are very small, okay? And the inductance and capacitance is pretty small. So if you've got 400 picosecond delay, electrical length, I'll call that, in your transmission line, but only 40 picoseconds of electrical length in your via, you can see there's such a disproportion there that you're not even going to see that impedance discontinuity of that via. You'll have to have a very fast edge rate to get to that, by the time you get to that via, for that impedance discontinuity to show up and really impact your signal quality. So that's why typically you really won't see people worry about the impedance impact of a via until you start getting into the multi-gigabits range. And then it does obviously start to matter there. So if you've got sub 25 picosecond edge rates and you're doing different types of SerDes design that are well above 5 or 6 gigabits, then you do need to be concerned about the impedance of the vias. Until then, what I worry about is the capacitive loading of the vias. So if you think of something like a DDR3 or DDR4 memory interface, and you might be transitioning a couple of layers because you're doing dense routing, and let's say you have a DQ net, a data net, and let's say there's like 3 or 5 vias on it, while that might not impact the characteristic impedance a lot, that's going to start adding capacitive loading, which can impact the signal quality. So it is important to include via models in your signal integrity simulations, and also to consider the capacitive loading impact on it. And really the only way to do that, and probably the best way to do that, is through simulation. Thanks for joining me today for this coffee break video. I hope you enjoyed it. If you have any questions or feedback, or if you have a topic that you'd like me to discuss next time, send me an email at tim@signalbytestech.com, and be sure to join us online at signalbytestech.com. Sign up for our newsletter, be notified of when we do another one of these videos. Now, I'm going to have another cup of coffee, and it's probably time for you to get back to work. I'll see you next time.